Thanks. Great. Well, I guess we'll get started. Hi, everyone. It's good to see you all again at the Energy Systems Seminar. So I'm very excited to introduce Konstantin Löffler. Today, Konstantin is a researcher at TU Berlin and also at DIW in Germany, the economic research think tank that you have in Germany. And he's done quite a lot on the energy transition and on energy system modeling and you know, how to make models open source and comparing different models. And then he's built his own model that he's using for a lot of people are using for a lot of interesting things. So I'm very excited to hear what you have to say. So you can take it away. Thanks.
Yeah, perfect. Thank you. Thanks very much for the nice introduction. So yeah, as we just now mentioned, I will be talking today mostly about the model that we, not me myself, but me and the team have been developing. So it's not a one person effort. Of course, these large scale models do need more manpower than just one person looking into these things. And it's completely correct that we have been developing this model over the last couple of years, and I will talk a little bit about where we come from, what the idea is, what the scope is, potentially go into some sample results. The issue is that I have 5 to 10 minutes less than I was expecting to, so I may have to keep some things a little bit short, but I'll try to push through it and not leave too much out. So, all right, so me and our model, we are looking into energy system analysis. So usually within this scope here of time frame, where you have then short-term models, which are more looking at stability analysis or seconds to days maybe, and other mostly then electricity-focused models as well, like power market models or load flow analysis, which look into days and years. We're usually located in the long-term energy system analysis. So we're usually looking into years and decades in the future. So usually the main focus that we have up until now is usually looking towards 2050. We're thinking about expanding that potentially even further out. But so usually we're really looking into generating insights to future energy system developments across the entire energy system. So with an integration of different sectors as well. So that's one of the most important points. Our model was called the Global Energy System, or GENeSYS-MOD for short. And it was created essentially as a spin-off or as a fork from osmosis, which some of you might know. It's the open energy system model. And this is essentially a framework from an open source community that has been expanded quite a bit. And to give you some like rough outline, like osmosis is essentially quite similar to Markov because those had the same core developer at the heart that was pushing these things. And osmosis is essentially just the open version. And back then, in the very beginning, we just translated osmosis essentially, or updated the GAMS version of osmosis to the newest version. We're still actively being a part of this osmosis community and providing support for the GAMS version. But at the same time, the issue was essentially that since osmosis is a huge community, development times seem to be or tend to be quite long. Things need to be discussed within a steering committee each year and so on. And therefore, we kind of branched off at some point because we wanted to expand the model in ways, and we wanted to essentially use the model for our research, and therefore we kind of made it our own separate version and have since then vastly expanded the functionalities. On the left-hand side, you can see a little bit of a representation, very rough representation. It's not 100% accurate because we had to essentially trim it down to make it fit into a graph. But a rough representation of the technologies and sectors that are included in GENeSYS-MOD. So what we have and what we're focusing on usually is then all kinds of renewable generation technologies that usually like generate renewable electricity. We obviously also include all kinds of conventional energy generation technologies, so all kinds of fossil power plants and nuclear. We include a vast variety of different energy storages. We both have electricity storages, but also other forms of energy storage, such as heat storages or gas storages. And we're usually looking into the demand sectors, electricity, transportation, and then heating. So these are usually the sectors that we're trying to cover. Sometimes we've had some applications that expand this a little bit, going more into detail on the industrial side, but this is like the general scope that we're usually trying to cover. From like, as I mentioned, from like a technical standpoint, we're based on this osmosis implementation, but since then we've been adding stuff on top of that essentially. And back in our first GENeSYS-MOD implementation, which was published in 2017, we kind of diverted from osmosis in a way that we changed a couple things. So there were mostly just changes in functionalities, because there were some things that we wanted to use differently that were specific to our analysis. And since then, we've been adding things on top of it, and essentially expanding different functionalities. I will go into detail into some of them at least. But for the most part, it has mostly been usually trying to expand the scope of the model, so to include more detail on different sectors. For example, also including more temporal resolution, so some more detail on time, because the basic setup, or essentially the setup that you would see with most osmosis models would be 6 time slices in a year. So you would have 3 seasons, summer, intermediate, and winter, and then just day and night. And this is of course very, very rough, but this is how we also started. And then with the second version of GENeSYS-MOD, we moved towards 16 time slices in a year. So we had 4 quarters in a year and then 4 daily time brackets. And since then, we've expanded this to now have a time series reduction algorithm in there, which has been taken from a power sector model that has been developed at our chair at TU Berlin. And that essentially allows us to take a full hourly time series. So now all our time data is in a full hourly fashion. And essentially this algorithm then is able to trim that down to a reduced time series that still represents the seasonal variations of the year and the minimum maximum values and so on. So you still get the relevant fluctuations within the year. And this is user defined now. So essentially you can now tailor this regarding your computational availability that you have. So if you have a large computing cluster, you might be able to run it at a much higher time resolution than other people. And this is essentially what we've been trying to do. And one thing that you also see every time is performance optimization, performance optimization, performance optimization. This is one of the most important things, because if you want to include more and more functionalities, at some point you always hit this computational limit. And therefore, this is also one of the most important points, usually trying to reduce the amount of computational requirements as much as possible, so that you can blow it up again because you want to include more detail. From a also technical but different standpoint, GENeSYS-MOD looks like this, and this is trying to represent a little bit what the inputs and outputs are of GENeSYS-MOD. So on the left-hand side, you see what inputs GENeSYS-MOD takes. And this is usually then, we take baseline demand data, so essentially demand within each energy sector. So for transport, this is usually in kilometers. For heating and electricity and so on, this is usually in terms of energy, so in terms of petajoules. We take in renewable potentials, we take in weather time series. We do usually take in capacities in a base year, so we're always starting at some point, and it used to be 2015, now usually 2018, where we take this as a base year with the existing power capacities, and we're trying to calibrate to get statistical, like the correct values that we would use to see in 2018, for example, there. Then we get sometimes political targets, so we can model either CO2 budgets, we can have annual reduction targets, we could have CO2 price, all of these things could be included there. And then of course, fossil fuel prices and generally like cost assumptions are inputs to the model. The model then takes all of these and essentially performs the optimization. The model performs a cost minimization, so we're trying to minimize the net present value of the total system costs over time. So it's just the discounted total system costs. To achieve this then, usually we're looking at, for example, how do we make sure that we can uphold a 2-degree climate target or so on, and then we're trying to find the cost optimal path towards that goal. To achieve this then, the model then decides on the optimal investments into new capacities, for example, in investments in generation capacity, storages, transmission lines, for example, and then it also considers the cost optimal energy dispatch, so energy flows and everything. And this is essentially what you see in the middle here. And of course, we again have this part that's on the supply side. We have the demand side, which I already mentioned again. And then we have various ways of sector coupling, either through direct electrification or through indirect methods, such as through hydrogen, for example. And then the results that we get out of GENeSYS-MOD are then, for example, the primary energy demands that are resulting to fulfill essentially these energy requirements. We see the sectoral demands as well. So we get the demand that is then, for example, electricity demand that is generated by, or that needs like electricity demand that comes from providing heat, for example, to households or so on. So we get the sectoral demands in there. We get the investment into technologies and capacities and so on, as I mentioned. We get the renewable generation and generally generation and energy dispatches. We would get then potentially fossil fuel phase out dates, for example. So as I said, if we're looking at, all right, what needs to be done to uphold the 2-degree goal, then we would see, all right, which sector needs to move first, what essentially would be the optimal investments into technology changes. So that essentially you would see, all right, in which sector, which technologies would make sense going forward. And then, of course, one thing that we also get as an output are then the CO2 emissions, which result from the energy mix again. And then, depending on the use case, you can either have an analysis of the endogenous CO2 prices, essentially. So if you set a budget, for example, then you would have a shadow value of CO2, and you could get this as an output. Or again, you could use the CO2 price as an input, and instead see, all right, well, how does that affect emissions, for example. So it's quite flexible in that regard, and you can do many forms of analysis with that. From a mathematical side, I already mentioned this. It's a cost minimization, so it's a quite normal objective function, I would say. So the objective function is essentially just we minimize costs over the entire modeling horizon for all different types of costs. So there's not that much to be said here. What we're also trying to be is as open as possible. At the moment, this is partially true. Because so while we have a public GitLab page where you can download the model, there's documentation and everything, unfortunately right now it's still in GAMS, which is still somewhat of a limitation because of course this is a commercial tool and is not available to everyone. So right now we're doing some work there as well of translating the model to an open language, to either then Python or Julia or mixture. We're kind of still in the process of working on this. But this is, again, then the next step to making the model really accessible to everyone. And the ultimate goal would be for the model itself and all the data to be available as a package, essentially, that everyone could just download and run and use as they please. And this is essentially what we're really trying to achieve here, because there is definitely a gap for this in the current research landscape, because there are plenty of models and actually also quite a few open source models, but especially on the data side, it's usually not that accessible. Looking into what we've done so far, as I mentioned, in 2017, we published our first paper, and that was on a global scale. And this is also why it's called the global energy system model, because back in the days, we started with a global application. So sorry for having the slides in German here, but out of picture. But this was essentially then a global application for 10 regions of the world. And the original research question was essentially, is it possible to have a 100% renewable energy system for the entire world in 2050? And since then, we've mostly been looking into regional case studies. So we've kind of zoomed in onto various parts of this world. And this is what we've essentially been doing over the last 5 years or so. So we've been doing some country-level case studies, some regional case studies. So, for example, one focus point, of course, is always Europe, since we're situated here and there's lots of interesting projects and so on going on. So Europe has always been a focus for us. Of course, Germany has also been a focus, where we've also looked at Germany at a federal state level. We've had an analysis of Mexico, Colombia, South Africa, Japan, for example, also one study, and we've also had some publications on China and India, each at a province or like state level there as well. So we've been really looking into various aspects of the world and of the energy system with each of the different challenges that each individual region brings. And again, the idea would be to bridge that back to the global scope again. So now with hopefully then the new model version that's in an open language, that will also enable us to have actually a data set that's available for the entire world, but which also includes all the regional data that we've collected through this case study, essentially to bridge all of this together into one bundle, so that you have all the regional detail, but at the same time still the global scope. And this is essentially what we're trying to move back to again, to get this name essentially correct again. I mentioned that we have added quite a few functionalities over the time, so I want to also present a couple examples of some of the things that we've added over time and some of the studies that we've performed. So one thing, for example, was also that we included a module. Quick side note here. We are usually trying to keep the model code in kind of a block structure, and then you have sometimes modules that you can either enable or disable as a user, essentially, and you can choose to do so. So it's like an option. And one thing that we added for a study, I think 2019, was, for example, that we introduced a reduced foresight module. So in the end, what we implemented there is that you now have the option to run a rolling horizon approach, so myopic foresight. And this was used here to assess the influence on short-term decisions regarding asset stranding then in Europe. So there we essentially had three scenarios. One scenario that was the baseline, which is the regular case that the model has perfect foresight over the entire modeling horizon. And then one case where it had reduced foresight, so always only this 5-year foresight period. And then one where we also included the fact that even if you have reduced foresight, the model still optimizes, like economically speaking. But in real life, decisions are not always like the economic optimum, but instead you have many interested parties and also politicians that want to get reelected and so on. And therefore, we have included a third scenario that also includes then political boundaries and essentially then some assumptions on feasibility, for example, by public acceptance and so on. And then we've compared these results and we've seen that, for example, then if you really only plan like for the next 5 years and you only have the short-term targets in mind, that you would see a significant amount of asset stranding in Europe, even more than we already have, because if we really want to take the 2-degree goal serious, or even better, the 1.5, then already now we would face significant amounts of stranded assets in Europe. Also, one thing that we've added is an ex-post dispatch model, because, as I mentioned, our model in the end is still running at a reduced time series. So in the end, we usually range between 36 to 120 time steps within 1 year. This is usually what we end up with the scopes of the model that we had, which is obviously still very far from an hourly solution resolution, which would be 8,760 hours. But what we coded instead is we have a dispatch model that you can run after the actual GENeSYS-MOD computation has finished. And that takes the capacities that GENeSYS-MOD decided on based on this reduced resolution and tries to see whether the electricity system is actually feasible still at an hourly resolution. And we have added quite a few additional constraints that take care of, for example, that peak demand is met and everything, to be sure that we reach a point where even though our model runs at a reduced resolution, we still get results that are reasonably close to feasible at an hourly scale. So usually what we end up with, for example, for the European project, openENTRANCE that we're currently running, we see that in the end, our results end up with about 1% unmet demand in a year, which, again, considering that our model only has like 36-ish time steps in a year for this use case, which is, I think, quite reasonable. But this is a nice tool to kind of visualize that and see what the actual dispatch would then look like. So how much curtailment would you have, how much unmet demand, everything. So that's something that we also implemented. One thing that we've also tried to take a look at, for example, is then socioeconomic factors. And this is something that we're definitely trying to expand as well. But one thing that we did, for example, for India, was that we, for example, looked into employment numbers. So we added an employment module that you can either run as an ex post analysis again. So essentially that it just takes the results of GENeSYS-MOD, of the runtime of the results. And then you see, all right, how much jobs would be generated through expansion of renewable capacities and so on. But you can also run it within the model, which might be relevant for some regions. We've had this as a case for South Africa, for example, where coal mining is very centralized within 2 states, essentially within South Africa. And the rest of the country essentially just use the electricity from the coal usually right now. But with the future energy system that we saw, is that it gets more and more decentralized. You see renewable expansion across South Africa, essentially. The issue was that there's a net gain in jobs, but a loss in jobs in the coal mining regions, which is, of course, a huge problem for politicians then to sell this to the general public. So this is why we added this also as an endogenous computation, because then we can set the constraint, for example, all right, uphold the 2-degree target, but make sure that there are no jobs lost within any region, for example. And then you would get a result that satisfies this constraint as well. And then it might be, for example, more politically feasible in this way. So these are kind of things that we're also very interested in and looking into, all kinds of socioeconomic factors. All right, this was very quick and 20 minutes. And now I also was asked or want to present some of the results that from the project that I mentioned, so from the openENTRANCE project. So we'll take we have 4 minutes to go through them, and then you can ask questions, and then I can still go into more detail if you have any questions. But so this openENTRANCE project has been going on since 2019. It goes until next year, and it's essentially a European Horizon 2020 project with many partner institutions. And we are using GENeSYS-MOD for the pan-European pathways there that are then used for several case studies and other models. The model setup is that we consider 30 regions, so mainland EU, plus Norway, Switzerland, UK, and we also include the Balkan regions, but those aren't modeled as single countries, but instead they're a group of countries. We're looking again at the time frame 2018 to 2050, and we're covering the sectors electricity, building, industry, and transportation. And then depending on the pathways, you have different pathway-dependent features. The main thing that you need to remember right now is 3 pathways are supposed to uphold a 1.5-degree target, and 1 is considered a 2-degree target. So gradual development is the 2-degree target pathway. And this is what, for example, then electricity generation and demand would look like as a result of GENeSYS-MOD for these different pathways. And I'll just quickly walk you through this because there's much information and little time. So what you see here is essentially then the development of electricity generation and demand on both sides of the graph for the different pathways. There are a couple of things that we can see here. I think the colors are a little bit tricky with the projector, but I'll try to explain. So what we see is that, for example, gradual development in the end ends up, the top part here is storages. So you will see those mirrored on top and the bottom because essentially they're not generating anything, but they're like essentially a net zero, but we still want to include them to the graph. So they're mirrored on here. And what you see here is that gradual development is the 2-degree pathway, which has the lowest amount of efficiency gains and societal change, ends up with the highest amount of demand. You would also see this then in primary energy demand and so on. And the other pathways are usually have some assumptions on, again, efficiency gains. Societal commitment has a shift in attitude in society. So, for example, a modal shift in transport and so on. And what we see is that essentially the input electricity demands, the light gray part here, this is roughly the same in all pathways. And then the rest of the electricity demand comes from sector coupling. So we see a large increase in electricity use for here buildings, industry, transport, and then electrolysis. So these are then the main points or the main additions of electricity demand within the different scenarios. And then if we look at, for example, sectoral results, the colors here are this green teal part is onshore wind, the dark green part is offshore wind, solar is yellow, hydro is blue, and then here it's nuclear and natural gas, but that's very difficult to distinguish on the projector. And then if we take, for example, a closer look into hydrogen. This is something that also the model then allows is, for example, then we could look at, all right, hydrogen production, how does it look like in the different pathways? Where does it come from? So one thing that's quite clear immediately is that, for example, in techno-friendly, we allow for imports from hydrogen from outside of the EU. We do not allow that in other pathways. So this is the reason why there is less electrolysis and then therefore less need for electricity generation within Europe. And we also see that there's usually hydrogen really comes into the mix in like 2030 in our model right now here, and then usually gradually increases towards 2050 in its use. What we can also show in the results then, for example, is how much storage is used for hydrogen. And essentially the takeaway here is quite clear. It's essentially the more electrolysis you have, here, that's always the light bluish part here in the hydrogen generation. The more electrolysis you have, the more hydrogen storage you also have. Because then essentially this kind of goes hand in hand to be used as a flexibility option then in the system. And one other part that we can show in the graph would then be liquefaction and regasification of hydrogen. And this is also a very interesting result that we got in these results, is that we consider, or we do not allow the model to use existing natural gas pipelines for hydrogen, like simply that, because there's, I think, a huge debate whether it's actually doable or not, and how much retrofitting would need to be done. So the model would need to invest into new hydrogen pipeline capacities to essentially shift or transport gaseous hydrogen across countries, and it does so for some countries, but for the most part, actually, it uses then liquefied hydrogen and essentially moves this via trucks, which is a very interesting result, I think. And I would have some results on transport as well, but I will just skip over them for now and end my talk because I'm already at 26 minutes. So thank you very much for listening. And if you have questions, feel free to ask. I'm very happy to answer them. Yeah, thanks.